Alright, what's up logic fans? Welcome to another video, Bivalent Logic Explained. Today we cover section 6.2 of the text, our second section on quantificational syntax, and here we introduce a brand new rule of inference, universal instantiation. Let's rock. Alright, so let's go ahead and take a look at this. So in the previous section 6.1, we saw that we could use our old rules like modus ponens and modus tollens and De Morgan's and so on in quantificational context, that is with quantificational sentences. However, we also saw that you had to be careful how you applied them. And it turns out that the old rules, modus ponens, modus tollens, and all of those are inadequate to capture all of the valid arguments, and so we have to introduce some new rules in addition to all of the old ones. So let's take a look at this argument as an example. Now, it has one premise and it's got a conclusion, okay? And the premise is everything is both F and G. So maybe it's saying everything is both round and green, okay? Now, so pick anything you want out of Santa's bag, okay? For anything you pick out, that thing you picked is going to be both round and green. Therefore, it follows that for anything you pick out, it is round, okay? Now, intuitively, that's a valid argument, right? From this follows. The problem is how can we go ahead and prove that this is valid? Now, as we saw in the last video in 6.1, right, it might be tempting to deduce from this just like this, right, just boom, and then you justify it by simp on 1, right? But we saw that actually you can't do that because simp is a rule that applies to conjunctions, and 1 is not a conjunction. 1 is a universally quantified sentence, so this simply will not do. And in fact, using just the old rules, there is no way to deduce the conclusion here, C, from the premise, even though intuitively we should be able to. So what we want to do is we want to invoke a new rule and some new rules that allow us to capture valid arguments like this and other ones besides. So what we're going to do now is we're going to jump into the first of those new rules, universal instantiation. There's 5 new rules total. This is the first of them. They each have their own section. And then if you're covering identity, as we are going to, you'll learn 2 new rules for identity as well. And those are covered in their own separate sections. So let's get started with universal instantiation and how it works. All right. So as we get into our new rules of inference here, today, universal instantiation, we've got to recall 3 important assumptions, okay? We make 3 important assumptions with respect to all of these new rules. And so in particular with today for universal instantiation. And I found it's best to go over with students these assumptions up front. They just sort of aid understanding. So all of these rules that we're going to look at, these new ones, involve these 3 classical sort of assumptions, okay? The first one is that we assume a non-empty domain of discourse. That is to say, we assume that at least one thing exists. So in chapters 4 and chapters 5, I allowed us to sort of talk about empty domains, and they're fun, and we can talk about vacuous truth, and students really enjoy this and sort of get a kick out of thinking about what it's like if we assume nothing exists, right? And what kind of logical inferences can and cannot be made. That's all well and good, but officially now that we're doing quantificational syntax, we no longer consider or entertain the empty domain. At least one thing exists, okay? And you're going to see how this plays out with universal instantiation very quickly. Second assumption, every member of our non-empty domain exists, okay? So we can have a domain, for example, of ghosts, but we assume that those ghosts exist. What they're like, what kinds of properties they have or lack, completely logically independent issue, but for our purposes, we're going to assume that whatever is in our non-empty domain, in fact, exists, okay? So don't let yourself get caught in wormholes that way. Another assumption is that every individual constant. So if you see like FA, for example, if you see a sentence like this, the individual constant A, as it appears in a quantified sentence, is going to denote some member of our non-empty domain, and it's going to be assumed that that thing in fact exists. Okay, which one it denotes might be a separate issue. Okay, but it denotes some member of our non-empty domain, and whichever member it does in fact denote exists. Okay, so those are the three big sort of assumptions that we make for all of our rules, and in particular today for universal instantiation. Okay, so now let's look at a particular example to introduce our new rule, universal instantiation. We're also going to call universal instantiation just UI for short, is how you're going to see it abbreviated. So universal instantiation, intuitively motivated, and we'll give the hard definition shortly. But let's look at this particular example. So this says everything, no matter what you pick out as Santa's bag, whatever you pick out is going to have the property F. Therefore, the particular thing A, if you pick that out, it's going to have the property F. So intuitively, that's a valid argument, right? From the universal claim, we can infer that the particular thing has it. So for example, if all swans are white, then any particular swan you pick out, A, for example, it's going to have the property of being white as well. And intuitively, that's a valid argument. How do we get from this to this? Well, we use the rule universal instantiation is what allows us to do this. It allows us to go from the universal, notice we have a universally quantified sentence, to a particular. So FA, and you would just write UA on 1, UI on 1, universal instantiation on line 1. So it allows you to make this kind of maneuver, and we would just write QED here to finish off our demonstration. And that's basically all there is to it conceptually, right? Universal instantiation allows us to strip off a universal quantifier and move down to a particular thing with no universal quantifier on it. Okay, I also want to note that we could have gone to B, we could have gone to C instead of A here, we could have gone to D, we could go to any individual constant we like. And notice that from our classical assumptions, right, we're assuming that there is at least one thing exists. We're working with a non-empty domain, so it's not like, this is vacuously true and then all of a sudden that's not true. All right, so you see the need for classical assumption 1, and we're assuming that A in fact exists, and we're assuming that the individual constant A denotes some member of our non-empty guaranteed to exist domain, right? So all the classical assumptions are coming into play. This could be B, it could be C, it could be anything. It can also be a pseudonym, as we will explain later. Okay, let's look at another example, and again, we're just looking at a couple of examples to intuitively motivate the rule universal instantiation. We will get to the precise articulation of it momentarily, but let's look at this example. In this example, you've got two premises. The first one says everything is such that if it's F, then it's G, and the second premise says that S is in fact F. And you're supposed to be able to conclude from this that S has the property G, and intuitively that is a valid argument. But notice, using only our old rules, you couldn't do it. You need a new rule, universal instantiation, in order to show this syntactically valid. So I'm going to give you a chance, without explaining too much more, to pause now and see if you can't figure this out. You have to use universal instantiation to do it, but pause now and we'll come back together. Okay, hopefully you were able to figure it out, right? But in this case, what we did was we universally instantiated 1 here, and unlike the last case, you have a much bigger thing. Instead of just fx, you have if fx, then gx, and notice we replaced x with s, okay? So in both cases, and that's going to be an important feature of the rule universal instantiation when we formally define it. But yeah, so everything is such that if it's F, then it's G, so it follows that the particular thing is S is such that if it's F, then it's G. So that's universal instantiation on 1. And then notice now you've got your really nice old rule modus ponens all set up. Once we've stripped away the leading universal quantifier, you're left with a conditional. This is a conditional. Here's its main connective, right? And you've got the antecedent affirmed in 2, and so modus ponens applies, and boom, you're done. And I want to emphasize, okay, that you can fill in S here as many times as you want. So if X appeared here like 5 times within the scope of this quantifier, then you could repeat S every time. And in fact, you would have to repeat it every time. You couldn't put S here and then like A there. You have to use the same individual constant throughout for every X that you're replacing, okay? And as many times as necessary. And don't leave any as an X if it's within the scope of the quantifier you're removing. In this case, we're removing this one, okay, or detaching it. Okay, great. So prior to formally stating the rule universal instantiation, we need to introduce a final concept here, and that's the concept of a pseudonym. Now, pseudonames come in 2 types. There are universal pseudonames and there are existential pseudonames. Today, we only need to focus on universal pseudonames because they are what primarily bear on the rule universal instantiation. But recall that the symbols A, B, C, D, all the way up to and including T stand for individual constants, right? So this is chapter 4 review. And then the variables X, Y, and Z, right? These are all individual variables that you see attached to quantifiers and so on, okay? But this misses the symbols U and V. U and V have been reserved up until now, and they were going to be used for universal and existential pseudonyms. So U by itself, or U sub 1, U sub 10, okay, so we have as many of them as we need. And then V for the existential pseudonym V, V sub 1, V sub I, which we'll discuss in further videos. Now, what is a universal pseudonym? Well, it behaves a lot like an individual constant, okay? So suppose I want to say something about all triangles, for example, or about everything. So I want to make a universal statement of some kind. Well, one way to do that is just to haul off and say all triangles contain 180 degrees, for example, okay? There's a different way of saying the same thing, though, that natural language has, and that's what universal pseudonyms sort of reflect. Universal pseudonyms allow us to say the same thing as saying everything is a certain way, like all triangles contain 180 degrees, but speaking as if we were talking about a particular thing. So, for example, we could say the arbitrary triangle U contains 180 degrees. So here it's almost as if we're talking about a particular thing, but since the particular thing in question, U, is arbitrary, right? It could be any triangle. It sort of has the same import and semantic content as saying all triangles contain 180 degrees. Notice we couldn't say the same thing by saying triangle A contains 180 degrees. A is an individual constant, refers to a particular one. So it could be that A, that particular thing, has 180 degrees, but that doesn't capture that any other triangle, every triangle has it. It's only when we say every triangle contains 180 degrees or any arbitrary triangle U contains 180 degrees. So it's kind of like an individual constant, but instead of referring to a particular one, it refers to an arbitrary, perfectly general one. And that's the role of the universal pseudonym. You'll get plenty of practice with this to come. And since we're getting low on time here, what we're going to do is we're going to move into the next video where I will officially define universal instantiation, and you'll see it references universal pseudonyms and pseudonyms in general. So we'll catch you on the next video for this section 6.2.